Well, I'm back. This time around, we're going to do one of the Chapter 8 problems near the end of the problem set. And I liked this one, problem 107 in Chapter 8, simply because, gosh, there's a lot of stuff in there. The problem has got all kinds of combined pieces in it, some of it that calls back to earlier chapters, and a lot of it concerning the Chapter 8 stuff. It gives us a compound of barium and nitrogen, tells us it's called barium azide, gives us the percentages, wants us to figure out the formula of the azide ion, draw the Lewis structure, see if there's resonance structures. If there are, decide which one is the best resonance structure. Based upon that, make a prediction about the bond lengths. Oh, I know, it's exciting. There's just so much going on in this thing. So we're going to work through all the various pieces of it here. It's kind of an example of how a lot of this stuff comes together, but particularly focusing on the Lewis structure and resonance structure components of Chapter 8. So here we go. First, we always look at the text of the problem. And they tell us that this stuff is a compound of barium and nitrogen. And so, as we've done in the past, I'm going to write its formula this way. I don't know how many bariums, I don't know how many nitrogens it has, but that's what we're going to figure out first. So I start off here with a little x and y, simply referring to moles. And I am told that we have 62.04% barium by weight, which translates into, assume 100 grams of this stuff. Get a good grams. 100 grams of this stuff, that means I've got 64.04 grams of barium. And so I'm going to turn my grams of barium into moles of barium. And I have to get the molecular or atomic weight of barium right off the periodic table. And looking it up on the table, 137.327. Remember, for these types of calculations, it really is not a bad idea to use all the digits the table gives you. There's 1 mole of this stuff. And when I set that up, and then when I just punch that out of my calculator, I'm going to get 0.4518 moles barium. And I repeat that calculation using the percentage of nitrogen, we're told. Grams nitrogen, ooh, I should say barium up there. Grams nitrogen. 1 mole of nitrogen, of course, is 14, and using all the digits on the periodic table, 14.0067 grams of nitrogen. Punch that out of my calculator, and I got 2.710 moles of nitrogen. So we have our tentative first draft of the formula. Barium, 0.4518. Nitrogen 2.710. And of course we have all these ugly decimals, and so we get rid of those by dividing by the smallest. And that gives me BA1N, and the calculator has 5.99 in the display. I think that's close enough to 6 to count. And so there's the formula. We aren't given any information about molecular weights or something, so we're going to run with this formula at the moment. Now, it does give us a bit of other information. It tells us that the azide ion has a -1 charge. In the problem. And of course, barium, sitting in column 2 of the periodic table, is itself going to have a +2 charge. And so I'm going to need 2 azide ions to balance out the charge. With 6 total nitrogens, it seems I'm looking at the azide ion having 3 nitrogens apiece in it. That's the -1 charge, and therefore I'm going to need 2 of them. And so yes, you could see the formula written BAN6 like we did here. I think it's slightly more accurate, taking into account the charges, to write it BAN3 subscript 2. Okay, and there is the formula of barium azide, and sure enough, you can look it up, Google azide ion. That is the formula. The azide ion is N3 minus. Okay? And so from this calculation and getting the formula of barium azide, we also now know what the formula of the azide ion is, which is the focus of the rest of the question. So I'm going to clear most of this out of the way, and now we turn our attention to the specific chapter 8 components of this question, the Lewis structure of this thing, the resonance structures, and all that good stuff. So the magic eraser, and we'll be back in just a moment. There. Now we're going to work on the Lewis structure of this thing, the azide ion, where we have 3 nitrogens, and of course that's going to imply one of them is in the middle, and the other 2 are out there as outer atoms. So I've written the 3 atoms down here. Of course, we need to know we need to know the total valence electron count. We have nitrogen, a member of column 5. There are 3 of them. And then remember, this is the azide ion. We have 1 more, and that's going to get us a total of 16 valence electrons. So 16 electrons, no more, no less, go in here. And so following the steps, we total up our valence electrons, put a pair between each. 1, 2, 3, 4. Okay. 12 to go. Outer atoms, make sure they have their magic electron configuration. Make sure they have their octet. 1, 2, 3, 4, 5, 6 on that one. 7, 8, 9, 10, 11, 12. That completes the octet of the outer atoms. They look great, but I realize I've just run out of valence electrons. I know, I really want to put more dots on the center. No, I cannot. I've run out of valence electrons. At a lesser university, they might put more dots on there, but not at Georgia Southern. And so we're stuck ending here. That means we've run out of valence electrons before the central atom is done. Yes, indeed, we start making double bonds and or triple bonds. And so you look at this, and there's actually 3 ways to make this thing work. I'm going to borrow an extra set of electrons from the nitrogen on the right, 1 from the nitrogen on the left, and I'll produce this structure that will have 2 double bonds. But I could also have taken 2 sets of the electrons from the nitrogen here on the right and moved them toward the central atom. So I could have done it this way and made a triple bond and left a single out here. Or I could have done the triple bond but to the nitrogen on the left. Each of these is a negative ion. So put the little brackets around everything and indicate the charge. And yes, indeed, these are the resonance structures. So there are 3 of them for this thing. One featuring a combination of single and triple bonds, another featuring the same combination, but with right and left exchange, and one featuring a set of double bonds. So there are the resonance structures, the Lewis structure and the resonance structures for the azide ion. The next part of the question then asks us, okay, if you got resonance structures, which resonance structure is best? And remember, that one gets into, okay, if you got these, combinations of doubles and singles and triple bonds in here, which one of these has the best distribution of formal charges? The lowest formal charges and if there's a choice between atoms, which there really isn't in here, they're all nitrogens, which one puts the negative formal charges on the more electronegative atom? That's not going to be a consideration because they're all nitrogens, but I am looking for ones that minimize formal charges. So remember the formula for calculating formal charges. You simply take the number, one we've used in class. For each atom, you look at the number of valence electrons that that atom would have. And then you take it and you subtract the combination of number of unshared electrons plus half the number shared electrons. You could also phrase that as number of unshared electrons plus number of bonds. That's the general formula for it. Now, for all of these structures, the atom that we're concerned with is nitrogen. That's a member of column 5. And so what I'm going to do is a sample calculation for this one for just a moment. It's a nitrogen, so the number of valence electrons is a 5, minus the combination of number of unshared, 2 plus half the number of shared electrons. There are 1, 2, 3, 4, 5, 6. 6 shared electrons. Half of that is 3. Okay. 5 minus 2 plus 3 is 5 minus 5 equals 0. This particular atom has a 0 formal charge. I turn my attention now to the central nitrogen in here, and it's going to have a different formal charge. Again, the valence electrons, valence electrons, this is nitrogen, column 5 of the periodic table, minus the combination of number of unshared, there are no unshared electrons in this one, plus half the number of shared electrons, 1, 2, 3, 4, 5, 6, 7, 8, okay? There are 8 shared electrons. This is 5 minus 4 equals positive 1, okay? Plus 1. I'll put a little circle around that. And finally, I'm going to do this nitrogen over here. Column 5, it's a nitrogen, 5 valence electrons is what the atom would have on the periodic table, minus number of unshared, 6, plus half the number of shared, 2 electrons, or only 2 electrons are shared on this particular nitrogen, half of that is a 1, okay. 5 minus 6 plus 1 equals negative 2, negative 2. Sure enough, the formal charges, a 0 plus 1 and minus 2, add up to negative 1, the overall charge of the ion. That's no great surprise. And if I repeated that over here, no big surprise here, that I would get the exact same formal charges on this one. If I run to this one over here in the center, and I repeat my formal charge calculations, and I won't go through the laborious process of doing that at the moment, they are going to come out plus 1, minus 1, minus 1, which again, they do add up to minus 1 overall. So we have 3 resonance structures with a different set of formal charges, and so the question, which resonance structure is best, is answered by which one of these has which one has the smallest formal charges, and that's this one right here. This one has a 0, but it has a negative 2, and that's not good on the grand scheme of things. And so what I'm going to do is look at this one. This one has the smallest formal charges, and thus this is the major contributor, the major resonance structure, the most important resonance structure. And so I have this one chosen. And the last question that they ask us here is, okay, give me a guess as to what the bond lengths are of the azide ion. Well, I could just make up a number, but what they're asking you to do here is essentially compare the average length of the nitrogen-nitrogen single, double, and triple bonds. And they're actually on table 8.5 in the text. And they are 1.42, 1.24, and 1.10. Those are all in angstroms. This from a textbook that says, oh, we must use SI units, and they go and use angstroms, which are commonly used in chemistry, but it's like, really? Not 142 picometers and so forth, but that's what the table gives us. And so, the question that they're asking here, okay, in azide ion, predict the bond lengths. I've got a mix of singles, triples, and doubles, but as we just mentioned, this is the major resonance structure. The average bond length of a nitrogen-nitrogen double bond seems to be about 1.24 angstroms, so that is going to be the answer to the last part for this particular problem. Predict the average bond length in the azide ion. Since the dominant resonance structure is the one with the double bonds, the average double bond for nitrogen is about 1.24 angstroms. That's going to be the answer for the question. What are the bond lengths of the azide ion? 1.24 angstroms. Man, so much stuff in here. Oh, it's just inspiring to think about. So there you go. A reminder of a percent composition question, formula determination, and then Lewis structure drawing, resonance structure, deciding which resonance structure is best by formal charges, and using that information and average bond lengths for the various types of bonds we encounter to get the whole problem answered. Not too bad in the grand scheme of things. So consider that, keep it in mind, go forth, calculate, and see you later.